you probably feel completely still right now.
I mean, most people do, yeah.
Right. Like whether you're driving or sitting at your desk or just, staring at the ceiling, there's this deeply comforting illusion of total immobility. We just trust the ground beneath us.
Oh, absolutely. It's human nature.
But I was reading this excerpt recently from a source called Ziko's Space Stories, and it it completely shatters that illusion with this mathematical reality that is frankly hard to shake once you hear it.
It's a terrifying number.
It really is. We, meaning you, the Earth, the Sun, the entire Milky Way galaxy, we are hurtling through the dark at over 600 kilometers per second.
Yeah. And just to put a terrestrial scale on that kind of velocity, and 600 kilometers per second, a trip from New York to Los Angeles takes, like, less than 10 seconds.
Less than 10 seconds.
Yeah. It's a speed that forces us to completely reevaluate our sense of place in the universe. I mean, we aren't static. We are in a state of constant extreme motion.
Okay, let's unpack this. Because the detail from the source that changes everything, the thing that really kicks off the deep dive today, is that we aren't just drifting aimlessly.
Right. We're not just coasting.
No. We are being violently dragged. There is this massive invisible gravitational anomaly that is pulling our galaxy toward a specific point in deep space. And astrophysicists call it the Great Attractor.
The Great Attractor. It remains, honestly, one of the most compelling mysteries in modern cosmology. We are dealing with scales and forces that make our entire solar system look like, I don't know, a single atom caught in a riptide.
It's just wild.
But to really grasp what this anomaly is, we first have to understand how we even know we're moving that fast to begin with.
Right, because if everything out there in space is relative, how do we find a speedometer for the entire Milky Way? The piece mentioned tracking our movement against the cosmic microwave background, which I always think of as kind of the ultimate Cosmere wallpaper.
That is essentially what it is, yeah. The cosmic microwave background, or the CMB, it's the residual thermal radiation left over from the Big Bang.
The afterglow.
Exactly. And because it permeates the entire universe, it provides this universally fixed frame of reference. It's a nearly uniform sphere of microwave light just surrounding us in every direction.
So if it's completely uniform, any movement we make relative to it would distort how we see it, right? Like it's the Doppler effect.
You've got it. As our galaxy races in one specific direction, the microwave radiation hitting us from the front gets compressed.
Right.
Its wavelength shortens, which we call a blue shift. Meanwhile, the radiation behind us gets stretched out, creating a red shift.
So by measuring the difference between the front and the back.
Right. By measuring the exact difference in temperature between that blue-shifted sky ahead of us and the red-shifted sky behind us, astronomers calculated that staggering velocity, 600 kilometers per second.
Wow. And when you trace the vector of that movement, it points straight toward the Great Attractor.
Straight toward it.
Which brings up the most obvious question, I think. We have these massive observatories that can image galaxies billions of light years away. We can literally look at the dawn of time. So why can't we just, point the James Webb or the Hubble out the window and look directly at whatever is pulling us?
Well, astronomy is completely at the mercy of perspective. The Great Attractor is located about 150 to maybe 250 million light years away.
Which is pretty close, right?
Relatively close in cosmological terms, yeah. But it happens to sit directly behind the center of our own Milky Way galaxy. It occupies a region of the sky that astronomers call the Zone of Avoidance.
The Zone of Avoidance. I mean, it sounds like a quarantine sector in a space opera.
It does sound like sci-fi.
But it's really just a massive optical blind spot. I was actually trying to visualize this earlier, and it made me think about standing in the middle of a really dense forest.
Okay, I like that.
Like, if I'm in the woods and I look straight up, I can see the clear blue sky, maybe a bird passing over. But if I try to look horizontally, right through the tree line, there are so many overlapping trunks and branches and leaves that my line of sight is completely blocked. I have absolutely no idea what's on the horizon.
That's a great way to put it. The trees in your analogy are the billions of stars, these thick molecular clouds, and swirling interstellar dust that make up the galactic disk.
Because our galaxy is flat.
Right, the Milky Way is relatively flat. So because we reside within that flat disk, looking toward the galactic center means looking through the thickest, most densely populated cross-section of our own cosmic neighborhood.
So the light just can't get through.
Exactly. Visible light from the Great Attractor simply cannot penetrate that wall of dust and gas. It is absorbed and scattered long before it ever reaches our telescopes.
It feels like the universe is deliberately hiding this monster from human eyes. It's like driving a runaway car at top speed in the pitch black, but your windshield is permanently smeared with mud, so you have absolutely no idea what you're about to crash into.
A terrifying thought when you frame it that way.
We are hurtling toward an absolute unknown, and we have a brick wall right on our windshield. We can feel the acceleration, we know the direction, but visually we are flying blind. So how are we mapping it? If the light is blocked, how do we know the Great Attractor isn't just like empty space and we're not just moving toward it by some cosmic fluke?
Well, we map it through gravity, specifically by studying something called peculiar velocity. Because in the grand scheme of the universe, everything is expanding. Galaxies are generally moving away from one another. We call that the Hubble flow.
The standard expansion of the universe.
Right. If you measure a galaxy's redshift, you can calculate how fast it's receding due to that expansion. But when astronomers started surveying the galaxies in our local universe, the ones relatively close to us, they noticed this major discrepancy.
They weren't doing what they were supposed to.
Exactly. These galaxies weren't just moving away from us as expected. They had an extra localized motion. They were drifting off their expected expanding paths.
Okay, so it's kind of like watching a group of cars on a highway. They're all generally driving forward, but you notice they're all subtly drifting into the left lane at the exact same time.
Yeah. And if thousands of independent cars are drifting into the same lane, you deduce there must be a massive off-ramp or, I don't know, a magnetic pull over there, even if you can't see it.
Right.
So astronomers measured the peculiar velocities of thousands of galaxies around us and found a massive convergence. Rivers of galaxies, millions of light years across, are all flowing toward this hidden basin in the zone of avoidance.
But wait, if those other galaxies are also caught in the pull, how do we see them if the dust is in the way? Are we just looking at the ones outside the zone?
Partially, yes. We extrapolate from the cross-traffic we can see. But modern astronomy has also found ways to sort of cheat the zone of avoidance.
Oh, really?
While visible light is blocked by the dust, longer wavelengths, like radio waves and infrared light, can actually punch right through it.
Oh, wow.
Yeah. Using radio telescopes, like the Parkes Observatory in Australia, scientists have started mapping the structures hidden behind the dust.
So we basically use radio waves to peer through the forest.
Exactly.
And when we map that out, the math starts to reveal the sheer scale of the anomaly. Because to pull our galaxy plus thousands of other galaxies at those speeds, I mean, the mass required is staggering. A single galaxy like our Milky Way has, what, a few 100 billion stars?
But roughly 100 to 400 billion stars, yeah.
Yeah.
Plus vast amounts of dark matter. It's a massive gravitational anchor on its own.
And the math indicates the Great Attractor has a mass equivalent to tens of thousands of Milky Way galaxies combined.
Tens of thousands. It is a concentration of matter so profound that it dictates the local geometry of the universe. To call it a heavy object is to completely misunderstand the scale. We are talking about a gravitational focal point that dominates a region of space hundreds of millions of light years across.
Which naturally leads to the theories of what it actually is, because we are completely blind to it visually, so we can only measure the math. And the Ziko's Space Stories excerpt throws out a few ideas.
It does.
And here's where it gets really interesting, because one of them immediately grabs your attention just because of how dramatic it is. The piece suggests that an anomaly this powerful might not be a standard cluster of matter at all. It posits that it could be a structural tear in the fabric of space-time.
A tear?
Yeah, essentially a cosmic sinkhole swallowing entire galactic empires.
I've seen that phrasing in popular media, and I get it. It definitely captures the imagination.
It's terrifying.
It is. But what's fascinating here is that we have to look critically at what the actual physics suggests. Because when dealing with an anomaly this massive that seemingly breaks our standard models, those extreme theories represent our desperate attempt to understand the incomprehensible. The space-time tear theory is, well, it's a bit of sensationalism.
Right, the sci-fi explanation.
It implies a fundamental breakdown of the laws of physics, a literal hole in the universe, which we simply do not see evidence for.
Okay, but when we talk about gravity, we're usually taught that basic analogy, right? Space-time is a rubber trampoline. You put a bowling ball on it, it dips, and that dip pulls things in. So the thought process is, if you drop tens of thousands of galaxies onto the trampoline, the rubber just snaps.
Right, right. The trampoline analogy is incredibly useful for early physics, but it falls apart at this scale. Instead of a two-dimensional sheet tearing under a heavyweight, think of space-time more like a three-dimensional fluid dynamic model.
Okay, fluid dynamics.
It's a non-Euclidean grid where mass dictates the flow of the fluid. The Great Attractor isn't ripping the grid. It's a massive natural convergence point within it.
So it's more like a localized densification of the fluid.
Exactly. The peer-reviewed, heavily supported scientific theory is that the Great Attractor is the dense central core of our local supercluster.
A supercluster.
Yeah. For a long time, we thought of galaxies as isolated archipelagos. But mapping those peculiar velocities we discussed earlier revealed that galaxies actually form an interconnected web. Gravity pulls galaxies into groups. Groups merge into massive clusters, and those clusters are connected by these vast filaments of dark matter and gas to form superclusters.
So we basically live in a supercluster, and the Great Attractor is essentially its downtown hub.
We call it the Laniakea supercluster.
Huh.
Laniakea is a Hawaiian word meaning immeasurable heaven. And the way astronomers defined its boundaries is fascinating. They didn't just draw a circle around a bunch of galaxies.
How do they do it?
They defined it by the gravitational watershed.
A watershed, like how rainfall on one side of a mountain ridge flows into the Pacific, and rain on the other side flows to the Atlantic.
That is the exact mechanism they used. They mapped the cosmic flow. Any galaxy whose peculiar velocity is pulling it inward.
For the Great Attractor.
Exactly. Any galaxy doing that is considered part of Laniakea. We are on one of the outer branches of this supercluster, and we are flowing inward. The Great Attractor is simply the valley floor where all the cosmic rivers in our local universe eventually meet.
So it's not a monster or a tear in reality. It's just a massive, crowded intersection of galactic clusters hidden behind our own galactic dust.
Right.
But, I mean, that still leaves the physical reality of the situation. We are flowing down the river. We are accelerating at 600 kilometers per second toward this immense concentration of mass. So crunch the numbers for us. When do we reach the valley floor? When do we actually hit the Great Attractor?
Well, if the universe were a static stage, it would just be a matter of calculating the distance divided by our velocity. We would eventually fall into the center and merge with whatever massive clusters reside there.
Okay.
However, the universe is doing something entirely different behind the scenes.
The stage itself is moving.
It is expanding. But more importantly, the expansion is accelerating. In the late 1990s, astrophysicists were studying distant-type Ia supernovae. These are exploding stars that have a very consistent, predictable brightness, which makes them perfect cosmic yardsticks.
Standard candles, right. Like, if you know how bright it inherently is, you can tell exactly how far away it is by how dim it appears to us.
Right. And what they found was shocking. The distant supernovae were dimmer than they should have been.
Meaning they were further away.
Meaning they were further away than the standard model of expansion predicted. The universe wasn't just coasting outward from the Big Bang. Something was stepping on the gas puddle.
And that something is what we now call dark energy.
Dark energy. It is arguably the biggest unsolved problem in physics today. It appears to be an intrinsic property of the vacuum of space itself.
So just empty space has this energy.
Exactly. As space expands, more space is created, which means more dark energy, which causes space to expand even faster. It acts as a universal repulsive force, actively stretching the geometry of the cosmos and driving galaxies apart.
Okay, so we have two fundamentally opposed forces acting on our galaxy right now. We have the localized gravity of the Great Attractor pulling us forward, trying to pull the local neighborhood together.
Yes.
But simultaneously, we have dark energy stretching the very fabric of space, trying to push the neighborhood apart.
It is a cosmic tug-of-war on an incomprehensible scale. Gravity dominates on a local level, which is why our solar system stays together and why we are currently being pulled toward the Great Attractor. But dark energy operates on the grand macro scale of the universe.
It makes me think of running on an endless treadmill. Like the Great Attractor is furiously pulling the belt forward and we're sprinting toward the front, but dark energy is physically stretching the length of the treadmill itself. It's pulling the console further away from us faster than the belt is moving us forward.
That's a brilliant analogy. And in this scenario, the math is very clear about who wins the tug-of-war.
Is it dark energy?
It is. The repulsive push of dark energy is currently stronger than the gravitational pull of the Great Attractor. The space between us and the center of Laniakea is expanding faster than our peculiar velocity can cover the distance.
So wait, even though we are moving at 600 kilometers per second toward this massive gravitational basin, we will never actually arrive.
Unless our understanding of dark energy fundamentally changes, no. We will never reach it.
That is wow.
The expansion of the universe will eventually rip the Laniakea supercluster apart. The gravitational bonds will be overcome by the stretching of space.
The river will dry up before we ever reach the valley. That is deeply ironic. I mean, the source material spends so much time focused on the dread of this immense, unseen monster dragging us into the dark. But the reality is an eternal limbo. We are forever falling toward a destination that is constantly receding from us.
We are caught in a permanent state of suspension. The doomsday scenario isn't a spectacular cosmic collision, it's isolation. Eventually, dark energy will stretch the universe so thin that the other galaxies will simply slip past our observable horizon.
It completely shifts your perspective. I mean, so what does this all mean for us? You step outside, you feel the solid ground, and you worry about your daily life. But zooming out, we are just tiny passengers on a ship sailing through a violent, mysterious cosmic ocean?
We really are.
We're caught in a swirling current, heading toward a massive waterfall that we can't see, only to find out that the river is evaporating out from under us. It is the ultimate humbling reality check.
It forces us to acknowledge the absolute limits of our perception. We don't know who is driving, and we don't know what lies ahead in the dark. We are completely blind to the very structure dictating our local cosmic flow.
Yeah.
But to truly underscore the scale of what we are dealing with, there is one final wrinkle in the data that we haven't touched on yet.
Oh boy. Go ahead. Break the universe for us one last time.
Well, we established that the Great Attractor sits at the center of the Laniakea supercluster, pulling on tens of thousands of galaxies. But as astronomers have gotten better at peering through the zone of avoidance and mapping those broader cosmic flows, they notice something else. The Great Attractor itself isn't sitting still.
Wait, you're kidding?
Laniakea, the Great Attractor, our entire local supercluster. The whole massive structure is also moving.
Are you serious?
It is being pulled by an even larger, even more distant gravitational anomaly located further out in the universe, a structure known as the Shapley supercluster.
So there's a bigger fish.
There is always a bigger fish.
The thing pulling tens of thousands of galaxies is itself being dragged by something even more massive. It's like Russian nesting dolls of gravitational forces. The scale just keeps expanding the further out you look.
It raises the ultimate question about the topology of our universe. How deep do the structures actually go? What terrifying, unseen force lies beyond our observable horizon, pulling the strings of the superclusters we can barely perceive? Are there even bigger monsters lurking just beyond our cosmic horizon?
That is the thought that lingers long after you close the book on this topic. We are charting these massive unseen currents, mapping ghosts in the dark, and every time we find an answer, it just points to a much larger, more mysterious force further out.
It's a never-ending puzzle.
The universe doesn't give up its secrets easily, especially when we're trying to look through the mud on our own windshield.
Yep.
But we keep mapping the flow, we keep measuring the cross-traffic. And to borrow the closing sentiment from our source today, Ziko's space stories, as you sit there, seemingly perfectly still, hurtling through the void, keep your eyes on the skies.